welcome everybody to this public lecture entitled Fashion, Faith and Fantasy. The lecture is organized by the Jagiellonian University, the Copernicus Center for Interdisciplinary Studies. And it is my great pleasure and honor to welcome here among us Sir Roger Penrose, the very great physicist, a very great scientist. And the typical characterization of great scientists is that sooner or later they put the pen on paper to share their fascination of science with others. And Roger Penrose is an author of several books in which he shares with us his fascination of science. And I think that perhaps 3 of his books are especially important. They, so to speak, mark his pathways through the ways of science. These books are, the first one is The Emperor's New Mind. In this book, Roger confronts the human mind with the pretense of computers to overcome human mind or even make it unnecessary. And according to him, the judge in this dispute are laws of physics. The last decisive word belongs to them. The second book, which marks Roger Penrose Road to Reality, is exactly the book entitled The Road to Reality. This is a comprehensive tour through the network of physical laws and their deep philosophical layers. And the third book is a new one entitled Fashion, Faith and Fantasy. This is a new book by Roger Penrose, and in this book, well, I will rather stop summarizing the master, because the master is among us, and I will give the floor to him in a moment. But before I do that, I must say that I already have made an acquaintance of this book, and I can assure you that for everybody who is not afraid of thinking, this book is really the book of 3 F's: fascinating, fantastic, and fabulous. The floor belongs to you, Roger.
I should explain that I'm here to honor Michael Heller's 80th birthday, so he is the reason I'm here, which is a great honor for me. I've only just realized there are 2 screens here, so this is a problem I always have with 2 screens. If I point at one of them, then people can't see on the other one where I'm pointing. So I shall have a problem with that. But this is the title of my new book, as Michael has explained, and it's aimed at certain trends in modern physics which one might question. And these are described by these 3 words that I have here: fashion, faith, and fantasy. Each one of them is particularly aimed at one topic in physics, in modern physics, but the words can be used more generally. I should explain that the fashion word has to do with string theory, and when I should say that the title was one that I gave to the Princeton University Press when I had been invited by them 13 years ago it was, to give 3 lectures at the in Princeton University, and I was a bit nervous about what I had to say, particularly because the world experts on at least 2 of the topics were in Princeton, and so it was probably a very foolish title, but nevertheless I probably was woken up too early in the morning and hadn't quite weighed up the issues at that stage. But to explain, first of all, the fashion, I want to say something about that. I should say that in mathematical physics, a very important driving force is the beauty in the subject. And it's certainly true that in many areas of theoretical physics one sees schemes of outstanding beauty, but it's the beauty which is often hard to appreciate because it's in the mathematics. But let me start by giving you a different example. I hope I can get this to work. I'm mainly using this to move the machine along, which is going to, I'm going to fail, I can tell, because it's not working even already. Now, what am I doing wrong? Why doesn't it move it? It's not been... I'm pressing the right buttons. Is there a turning on button I should press? It's on? Yes. Thank you. I push. It's just weakness on my part. Okay, so let's just see. Yes, that works. Okay, this of course is a theory of physics, which was a very ancient one. You have to go back to Greek times, time of Plato and so on, and we have a very beautiful description because these are in terms of the Platonic solids, which are very beautiful mathematical structures. So we can see at the top, well, I'm mainly going to describe by words, I think. We have at the top left, we have the tetrahedron, which is supposed to, I should say that it started off when there were 4 elements. It was considered that matter was composed of 4 different substances. Fire, that was the tetrahedron. Air was the octahedron, and water, the icosahedron, and the cube was earth, or solid material. And it sort of had some relation to solid, liquid, and gas, and perhaps plasma nowadays one would think of as a 4th state of matter. They didn't know about the dodecahedron, and when the dodecahedron was discovered, they had to decide that there was another element, you see. So this is an example of modifying your theory in the face of new observations, which I suppose is something that people do. I should say that when I first heard about these ideas, it seemed to me it was a very beautiful thing, these solids, but what's it got to do with predicting anything? It's a little bit more than that, because if you take 2 cubes, you can cut them up and produce 1 octahedron and 2 tetrahedrons. It's a little exercise you can go home and try. And the thing is, it explains, if you take 2 sticks, well, those sticks are made of solid material, and so you rub them together in the right way, and you produce fire, that's the tetrahedron, and smoke, that's the octahedron. So it does have prediction. As far as I know, that's the only prediction it makes. But it's a very beautiful idea. Well, let me fast forward a bit. Well, first of all, let me say that there was a better theory of fire a few centuries ago, which was the phlogiston theory, which was basically, as we would now understand, negative oxygen. But it was disproved by Lavoisier, basically, although his ideas weren't altogether very good, too. Nevertheless, the idea of that was a better theory of fire, but not as good a theory as we have now. And you might say, well, modern theories aren't influenced by such things, these fashionable ideas. But I wanted to complain about string theory, which was my reason for the fashion part of the book. Now, let's see if I push the thing hard enough this time. No, I pushed the wrong one too hard. Okay, there we go. Now, you see, first of all, let me explain what these diagrams are. These are what are called Feynman diagrams. And here, you should think of these as space-time pictures, roughly speaking. And the upward direction is time. So I've got time going upwards. This is because I work from relativity theory, and people who work in relativity theory like to have time going up. But particle physicists like time to go from left to right. So I apologize to the particle physicists that I'm using the relativity version of the direction of time. But these are just examples where you think of particles doing, the first one is 2 particles coming together, making a third one, and that splits into 2 others. And then these are other little processes of that general kind. And each one of these diagrams represents a calculation. This is a very specific mathematical expression. And they work very well. The main problem is, if you take the one at the end, you have these closed loops of lines. And when you have these closed loops, this is where the theory actually starts to get interesting and where quantum mechanics starts to have a real role to play. But the other problem is that when you have these closed loops, you tend to get answers which are infinity. And infinity is no good, because that's not the real answer. So there are all sorts of tricks that people use to get rid of these infinities. Very, very clever tricks, but nevertheless, it's not very satisfying that you have to go through these tricks which aren't really part of the initial theory. You have to invent different ways of extracting finite answers out of expressions which are, strictly speaking, infinite. Now, the thing that I was explained an idea by Leonard Susskind in about 1972, I think it was. And let me make sure I can get this thing to move. I'm moving it the wrong way, apparently, by the look of it. Yes, now what's happening? Here we have. This is an idea which I found very beautiful when I first heard about it, that if you think of so imagine in those previous diagrams, the particles are like points, and they move along, and then something happens, and they split into two, or something like that. But the trouble is you get infinite answers, and you might think of that as something to do with the fact that these have got corners on them and so on. It's a bit more complicated than that, really. But nevertheless, if you smooth them out, and the idea here is that instead of having the particles being single points, they're little loops. And then you can imagine these sort of plumbing arrangements where they join up and produce these smooth surfaces. And this connects with a very beautiful idea in mathematics, which is what's known as Riemann surfaces. And it's something which is very close to my own heart, the kind of mathematics that's involved in these Riemann surfaces. And this is the idea is that it makes these infinite answers finite. And it does do a good job at doing that. So I found that very attractive. And I was most impressed by this idea when I first heard about it. I thought, that's great. And I was trying to relate it to some other ideas that I had of my own. But then it didn't take long before people discovered that these things didn't really work unless the number of space dimensions was increased from 3 to 25. So you had to have 25 space dimensions. And when I heard about that, I said, well, okay, try something else. But it didn't affect other people this way, mainly because the sort of picture that was presented was that, all right, there were 25 space dimensions, but 3 of them were sort of big in a sense, and the other ones were tied up into a little... I'm not very skilled at this. Not at all skilled at it. There we go. The picture that was presented, that the other dimensions were what they call small. Now, what that means, it's a little loop. And the example here is of a hose pipe. This hose pipe, if you stand away from it, it looks one-dimensional. You think of that one dimension as corresponding to the 3 dimensions of ordinary space. But when you get close, you see the surface of this hose pipe is 2-dimensional. You need a magnifying glass here to make sure you can see that it's really got a 2-dimensional surface. But because it's wrapped up in this little loop, you don't really experience it. That's the idea. And so the extra 25 dimensions will be all wrapped up in these little loops, and so you don't see them. And that was the explanation for why you get away with these extra space dimensions. And that's still the argument that's presented in string theory. Now, one reason that I didn't like it was that there was a certain idea which I had found very powerful in developing my own thinking, which is the idea known as functional freedom. Now, I want to give you a little bit of a digression for the moment, but it's trying to explain the ideas of functional freedom. So let me try and do that, well, except that I'm going the wrong way again. Here we go. That's better. Now, let me try something very elementary, first of all. The idea, when you raise a number to a power, suppose you say a to the b, as we have at the top line there, then that is a times a times a times a, b times. So we're all familiar with that notion. The b is a little b at the top, and that's what it means. You might consider doing that twice. So you're raising a to the b to the c. The printers don't like it very much because you've got to find a little letter which goes 2 steps up and so on, and the computers don't like it very much until you learn how to do these things. But, of course, it's fine. And that means it's a times a times a times itself, b to the c times. In other words, it's b to the c, a to the b to the c. You have to remember it's b to the c go together, and it's a to the b to the c, not a to the b to the c. And you might say, well, if you did a to the b to the c, then the third line down, you can rewrite that as a to the bc. And so there's not much point in interpreting it that way. So you really mean it's got to be a to the b to the c, that way around. And that's what it means. Now, examples of this are quite familiar. The notion of a googol, this was, I think it was the nephew of a mathematician, Edward Kasner, and his nephew had an idea of writing down a really big number. And this really big number, you write down 1, 0, 0, 0, 0, 0, and if there are 100 zeros, that was a pretty big number. And you might say, what am I talking about numbers of that scale? It actually does come in to the considerations in the book. It's purely sort of coincidental, but it happens to be, we have galaxies in the universe which have, as far as we know, pretty well all galaxies have huge black holes in their centers. Our galaxy has a black hole which is about 4 million times the mass of the sun in its center. And when the universe expands and expands and expands and expands and gets very rarefied, then these black holes will start to evaporate away by the Hawking evaporation process. And it's a very, very slow process because black holes are extremely cold. And you've got to wait till the universe is much colder than the black holes. And it takes about a googol years for the biggest of these black holes to disappear. So that's where the googol comes into the considerations in my book, because it is relevant. You have to worry about how long it takes for these black holes to disappear. And it takes about a googol years. Well, this little boy wasn't very satisfied with that. He wanted bigger numbers than that. And so with some discussions with his uncle, they produced this number called a googolplex. And the googolplex is 1 to, you write 1 first, and the number of zeros is now googol zeros. So it's 10 to the power 100. So it's one of these double exponents. And this is a really big number. You might say that couldn't come into the book. Well, it does. In fact, a number comes into this book which is a lot bigger than that. It's about a googol raised to the power 1,000,000, million, million, million. And that is about, what is the use of that number? Well, it's a measure of how improbable the Big Bang was. I don't mean that the Big Bang was, well, the Big Bang could have been lots of kinds of bang, you see, and it's a very special one. And this very special one, how special is it? Well, that's about a measure of how special that Big Bang was. And that also is something which I talk about in the book, and it plays a big role in things that I do, not in the fashion chapter, but in the fantasy chapter, but mainly. Now, let me see again if I test my skills about moving this to see whether I've learned anything. I've learned a little bit. Now, you see, one of the features about this is that when you have double exponents, it's the number at the top which is the important one. And the ones downstairs don't matter too much. And as an example of that, if you consider this googolplex, which is 10 to the power 10 to the power 100, or, well, actually it's 10 to the power 10 to the power 124, which is the number measuring the unlikeliness of the particular kind of Big Bang which seems to have had, if they are to have been chosen randomly, which is the question. Now, of course, it wasn't. That's more or less to say it wasn't random, but that's the kind of thing that you have to consider as numbers of that scale. But really, the first number shouldn't have been a 10. It should have been actually E. Never mind about that. But if you make it 2, which is even smaller than E, you see it doesn't make much difference, because it's still 10 to the power 10 to the power 124 is 2 to the power 10 to the power 124 point, whatever it is up there, I can't quite see it. But you see it's almost the same number. The top number is hardly affected by the bottom number. You can change the bottom number a lot, and the top number is the all-important number. So you bear that in mind. And when these numbers get bigger and bigger and bigger, it becomes more and more that it's the top number that's important. And this is the real point in what I want to say. So let me try and move ahead on this. See if I can. Now, I'm going to talk about when these numbers become infinite. Now, there is a very famous theory of the infinite, which is due to Cantor. And I want to say that this is not Cantor's theory that I'm going to talk about. Because Cantor's theory, a particular example of it here, I show, if you want to, you can consider the number of natural numbers, that's 0, 1, 2, 3, 4, 5, 6, and that's in a certain sense the smallest infinity. But if you consider pairs of numbers, say pairs of natural numbers, Cantor says, well, there aren't really any more of them than there are just single natural numbers. And one way of seeing that is you make a plot of all the pairs of natural numbers, and then Cantor shows how you can count them all by just going back, wiggling backwards and forwards, and you can simply count them, so that the number of pairs of natural numbers is just the same as the number of natural numbers. And this is, at first sight, a rather remarkable fact, but nevertheless, that kind of thing is the basis of Cantor's theory of the infinite. But that's not what I want to talk about here, and you can sort of see what one of the troubles with this is that it's not continuous. That is to say, you can take two numbers. I won't try pointing at them because, again, I shall probably miss, but I can't point at both screens at once. So let me not do that. If you look at the top left-hand corner somewhere up there, you will see where the numbers go wiggling down and then back again. You have two pairs which are very close to each other, but they're a long way away with regard to the counting system. So the counting system is very far from being what you might call continuous. And the kind of infinities I'm talking about here will be where you respect the continuity. And the sort of idea that I want to talk about is, I hope that's the right slide, where you might consider, say, the number of points on a curve or a straight line or a one-dimensional thing is supposed to be less the number of points on a surface, because you can't count them, the points on the surface, continuously. I mean, you can make a line wiggle around very densely on the plane, but it's not continuous. So you have this problem if you want to talk about infinities in the continuous way. And it means that you need something beyond the Cantor theory. Now, this theory is not new, I should say. It was basically developed by the great French mathematician Élie Cartan in the early 20th century. And it goes back to ideas of the Italian geometers also, which make use of this kind of idea of continuous infinities. Now, so here, if you have a plane, then I would say it's infinity. I'll put the infinity symbol, infinity to the 1, if you like. If it's on a line, if it's in a plane, it's infinity squared. You need two coordinates for it, if you like. If it's on a three-dimensional space, infinity cubed. An n-dimensional space, it would be infinity to the power n. Now, you see, I want to talk now about double exponents. Why do I want to do that? Because I want to count not just the number of points on the plane or the surface, but the number of functions. So, first of all, at the top left, we see a graph where it's discrete both ways. So you have the x-axis takes b discrete values, and the y-axis takes a discrete values. And the number of functions, the number of graphs, if you like, well, you see the first point for the x-axis, you have A possibilities. The second one, you have A possibilities. The third one, you have A possibilities. And you have B of them altogether, so it's A to the B. The number of possible functions for these discrete numbers is A to the power B. Now let's suppose that these are not discrete, but you're looking at spaces of different dimensions. And so you're looking at the space is the thing, the x-axis, if you like, and that can be a continuous space which has C to the D points in it. And the y-axis has got A to the B points in it. So how many continuous graphs are there? How many functions are there? Well, it's A to the B to the B to the C, if I have it the right way around. A to the B to the C to the D, sorry. So that's A to the B, C to the D. And that is, well, I'll give you an example of that sort of thing, if again I can make this work properly. Here we have a picture which is supposed to represent, say, electric fields in ordinary three-dimensional space. And you want to know how many electric fields are there in three-dimensional space. Well, it's infinity to the 3, infinity to the 3. So let me try and go backwards. This is testing my skills here. The bottom line is showing you infinity to the 3, infinity to the 3. That's the number of electric fields that you can have in ordinary free space. The top 3 is the dimension of the space. The bottom 3 is the number of degrees of freedom in the possible electric fields at any one point. So that's the number of components that the field has. But the top number is the really important one. So what I want to say here is if you want to count the number of fields that you have on a certainly, say, A to the B, C to the D, if the space dimension is the all-important thing. So what you see, I can't quite read what the top thing says, but let me explain the second line, I think. What I'm trying to say is that the first point is just saying that the number of points in a higher dimensional space is more than that in a lower dimensional space. But if you're looking at functions in those spaces, in other words, fields in those spaces, say electric fields or magnetic fields or electromagnetic fields or gravitational fields or what it happens to be, the fields have a certain number of components. That's the lower number in the exponent. But the dimension of the space is the higher one. And that's all important. It doesn't matter much about what the lower number is at all. Everything depends on the higher number. So if you have a higher number of dimensions of the space, then how many components that field has is totally irrelevant. And one may talk about counting numbers of degrees of freedom or something like that, and that is completely swamped by the dimensionality of the space. So if you're talking about fields in higher dimensional space, there are all these degrees of freedom, no matter how many numbers you have and say how many components your field has. That's utterly trivial. The dimension of the space will completely swamp everything. So how could the physics, which has extra dimensions in it, spatial dimensions, where they're taken to be ordinary spatial dimensions, how is it that you don't see that? And this was my gut reason, if you like, for really not believing in these high dimensional theories. Now, let me continue and address this question in the way that people did. People said, well, this idea is not new, because not that long after Einstein produced his general theory of relativity, which is a wonderful and very well confirmed theory these days, because we know from the LIGO experiments that there are gravitational waves which seem to be being produced by the swallowing up of pairs of black holes, or both kinds of predictions that came from Einstein's magnificent theory. I should say not predictions that Einstein would have liked very much, because his theory was magnificent, but Einstein himself didn't, I think, fully appreciate the power of the implications of his own theory. Nevertheless, these were early days, and a lot of people had doubts about Einstein's theory, but it wasn't so much that I want to address here. It seemed to be limited to the idea of describing gravity in terms of curvature of a space-time. Now we're putting space and time together, so we have a four-dimensional space-time, but the functional freedom is always in the number of space dimensions, because the field equations are supposed to carry these initial, what you're doing in one time progresses through the field equations. So the functional freedom is the number of space dimensions, not the number of space-time dimensions. But here we have a theory which was produced by Kaluza originally. I guess people call him a German because he was born in a place which was now part of Poland. Isn't that right? I've got it the right way around, but it was then part of Germany. I think I call him Polish-German. I hope that's all right. But anyway, it's a very beautiful idea that if you go up and have a five-dimensional theory, you can incorporate electromagnetism together, that is, in accordance with the very famous and wonderful equations of Maxwell, which describe electromagnetic fields and light, wonderful set of equations, and the theories, together with how they curve space-time according to Einstein's theory, is incorporated in this five-dimensional theory. A very elegant idea, but the problem is, how do you understand space-time being five-dimensional? Well, you see, in the Kaluza theory, what I'm trying to emphasize here is that it's not really a space in 5 dimensions where you have the full freedom in the 5-dimensional space, because it's restricted to where you have a symmetry in that extra dimension. So you see these little K's pointing up there. Those you have to imagine that in a certain sense above each point there is a circle, and the full 5-dimension is this whole family of circles sitting above the 4 space-time dimensions that you have at the bottom. And so the whole thing is a 5-dimensional space. But you're not really thinking of it of a 5-dimensional space, because there is no freedom, there's no functional freedom in the extra dimension. So that's the way the theory was presented originally by Kaluza, and I think it was Klein who had the idea of making it very small, like the hose pipe that I showed you before. But the string theorists like to think of those extra dimensions as fully dynamically. They're allowed to all sorts of vibrate in all sorts of ways, and so now you really do have a problem with the functional freedom. Well, I raised this question with people some years ago, and in particular, there was I think a year before I gave my Princeton lectures must have been in 2002, I think, when I went to a conference in Cambridge. It was really the last day of this conference, where the conference was honoring Stephen Hawking's 65th birthday or whatever it was. And I was at another meeting before this, and then I went for the last day, and I gave my talk, which I was describing my little problems with the extra dimensions, and I rather said that I didn't expect to get out of the lecture room at the end without being tarred and feathered. Perhaps I didn't have tar and feathers ready to do this. But the next day, it was quite interesting, because the next day I came to there was another meeting following it, and I was immediately Gabriele Veneziano, who was one of the founders of string theory, somebody I always get on with very well, and he was complaining about something, and then I said, no, I didn't mean that, it was so-and-so. He said, I see. And that moment, Michael Green, who's a very important figure in string theory, came up to me and started complaining about something, and then Gabriele Veneziano said, no, he didn't mean that, and they started arguing with each other, so I snuck off them. But at the same meeting, I sat down at lunch, and Lenny Susskind, the person who told me about strings originally, sat down opposite me, and he said something almost exactly word for word, as far as I can remember, was, "You're completely right, of course, but totally misguided." And I wasn't quite sure what to make of that, but I've still been puzzling over that ever since. But I should point out that the issue was this functional freedom issue. And let me try and say really the way that people... This is just another example of the Kaluza-Klein type of picture. It's what's known as a fiber bundle, and the one on the right-hand side is basically showing you what it means. You might have a space of some kind, that's the base space. You might think of that as space-time, that's the M thing. Then you have things called the fibers, and those are these spaces at the top. And a fiber bundle is, in words, basically an F's worth of F's. So an M's worth of F's, if I said it right. So the base space, you say, it's an M's worth, that's the M, of F's. And that's what it is. You have a collection of F's, and how many do you have? Well, it's an M's worth of them. And that is what a fiber bundle is. And the first example is just showing how a graph in ordinary physics is generalized to this very notion of a fiber bundle. It's a very important idea in physics, and I should say Andrzej Trautmann, a very distinguished relativist in Warsaw, was the person who really understood how the theories of physics, what are called gauge theories, which depend on this notion, really are theories, connections on bundles. I won't go into that because it's not what I want to talk about. It's perfectly respectable. I have no problem with that at all. It's a very important idea in physics. That's not really what I want to talk about. This is just to show you examples of what the Kaluza model really was. Now I'm having my gain trouble of trying to make this thing work. Here we go. Now people would say, you see, well, the reason you don't see these extra dimensions, or why don't you see all those degrees of freedom waiting to be excited? Why don't you see that? Well, the argument is the amount of energy you would need to excite them is enormous. And so that's why you don't excite them. What does enormous mean? Well, I think the idea is, because these were no doubt people brought up with particle accelerators and so on, that you would need an energy in a particle accelerator which was individual particles having an energy of something like a powerful artillery shell. So that's far beyond what could be done in ordinary accelerators. So the argument was, okay, that's fine. You'll never have to worry about energies of that nature. Of course, you don't know what's been done in the Andromeda Galaxy. Maybe somebody up there has produced such an accelerator. And the problem I have is, it's not like particle physics where you're trying to excite a little bit of an energy here. If you're exciting those extra degrees of freedom, it's for the entire universe. So one quantum entering that extra dimension is for the entire universe. And in terms of the entire universe, that amount of energy is trivial, utterly trivial. And here is the example that I gave I'm not sure I gave this example in my lecture in Cambridge, but it's certainly one that I did give in my lectures later on, I think, in various places. You consider the amount of energy that there is, say, in the Earth's orbit around the Sun. Well, again, that amount of energy is I don't know how many millions it is, more than the energy you would need to excite those extra dimensions. And that spread over the orbit of the Earth is an utterly trivial change in the extra dimensions. So you would be hardly changing it at all. And if you wanted to change it by a significant amount, you would need many, many, many quanta. And therefore, if you're going to need huge numbers of quanta, you might as well treat it as a classical problem. So it seemed to me that this argument that the energy is too great to excite is completely wrong. And I never could understand why people were complacent enough to think that you couldn't excite these extra dimensions when you've got the whole universe to play with to do that. And this so-called Planck energy, which is the artillery shell I've just been mentioning, is tiny. Anyway, that's the sort of argument that I was making, and nobody paid any attention to me after I didn't get tarred and feathered, but it was more the silence, which is in a certain sense more dreadful, because it means people are not paying any attention to you. Maybe if I was tarred and feathered, it would mean that there was more attention paid than it happened to be. But anyway, that's what I'm talking about in the book. Let me just say, I do think that there is an enormous amount in string theory which is very elegant mathematics and has a huge impact on mathematics. So it's certainly, in certain respects, a subject well worth studying. But there's no evidence that it's physics. And so that's the point I'm trying to make here. Okay, I'm not saying you shouldn't do string theory with these high dimensions, because, as I say, there's a lot of beautiful stuff in there. But as a theory of the physical world, I can't see it hanging together. And that was the point I was trying to make. Okay, now, what about the faith? Well, it's completely different. I've been talking about a theory, string theory in higher dimensions, where arguments that other people have tended to make, who don't like string theory, they would say, well, it doesn't have any implications which are testable by current physical apparati. There is no prediction that the theory makes which you could test. Okay, that's true too, but that wasn't my argument. My argument was that even if you could test it, it's not clear. It's not a theory which hangs together as a physical theory. That was my problem with it. Whereas the point of the faith is completely different. I'm talking now about quantum mechanics. Quantum mechanics has an absolutely enormous amount of support from observation. In fact, it was completely the other way around. People didn't want a theory of that kind. It was just the observations that drove people. And here's a good example of the sort of thing, one of the archetypal experiments. You have a quantum particle. It could be, say, electrons or some other particle that is sent, or could be photons, sent through a pair of slits, and these are two parallel slits. The second picture, if you close off one of the slits and you open the other one, and you see the particles behave like particles because they make individual impacts on the screen, which are more or less concentrated along the line through the slit. If you open the other slit, close the first one, then you have a very similar picture, just shifted a little bit to the right. But if you open both slits, instead of adding together these two pictures, you have a picture which is completely different. You have cancellations in some places and adding up in other places. And this is showing that in some sense, the particle is going through both slits at once, and you have to think of it in some sense as a wave instead. And this is one of the little problems that people were confronted with, and so quantum mechanics grew out of that idea. But obviously huge amounts of observational material which are explained by quantum mechanics and which we had no idea how to explain it. Things like the stability of atoms, which was an important one, spectral lines of atoms, all sorts of things. This laser pointer, which I've stopped using, but which is a nice example of that. You see, I was afraid of that. I press the wrong button if I do it. Yeah, no, if I point at it, you only see it if I point at the right screen. Let me not do that. Now you see, quantum mechanics, as we understand it, as the formalism tells us to use, what it tells us to use is that the particle, if it's an electron or whatever it is, has to be considered that it feels out both slits at once. Or in a certain sense, its state actually has the particle in both situations at once. So the particle goes through both slits at once. Crazy idea, but nevertheless, that's what you do. You have to consider that the state of the particle, whatever that state means, involves what's called a quantum superposition of two alternatives. And that's what you do in quantum mechanics. Well, that's fine, and it gives you all these things, works very well. Neutrons, you get very clear evidence that they must be feeding out these two routes at once. They seem to be going both ways at the same time. Well, you get used to that idea. It's a strange idea to get used to, but nevertheless, that's what you have to do. But the problem, of course, was one that Schrödinger himself was clear to point out, that his equation, that's the quantum state, how that evolves in time, tells you that if you had a cat instead of a quantum particle, that cat would have to be, well, in his example, it was dead and alive at the same time, and he's more or less saying, well, his theory, quantum mechanics, his equation, he was saying more or less, my equation tells you you can have a cat which is dead and alive at the same time. That's nonsense. Therefore, there's something wrong. We don't have the full theory yet. So Schrödinger and Einstein and de Broglie and even Dirac, if you look at the right place, who was the one who really formulated the form of quantum mechanics that everybody uses in physics. If you read the right thing in Dirac, you will see, and I have a nice quote in my book, he says, the quantum formalism works beautifully, but it is a provisional formalism. There must be some theory which comes to supersede it at some stage. And that's really the point I'm saying. It's the faith that quantum mechanics in its current form will persist, and that theory must not be questioned. And I think you find a lot of that, especially when you have experiments which have to do with black holes and so on, and people are led down a route which to me seems to me the wrong route, because they believe that you mustn't monkey with quantum mechanics because it works too well. Well, my version of Schrödinger's cat is a bit more like the two-slit experiment. The cat is going to get some food, which is you can see it in this room here, and the room has two doors, and there is a thing called a beam splitter. You see at the top left, there is a laser which emits a single photon. That photon encounters the beam splitter. Think of that as a half-silvered mirror, so that half the light goes through, half the light is reflected, it goes straight through. And in quantum mechanics, you must think of the photon as doing both at once. So it goes through and it is reflected. And those two alternatives, one of them opens one door and the other opens the other door. And if you follow the equation of Schrödinger, or what's called unitary evolution, if you follow that evolution, you have to believe that the doors are also in a superposition. There isn't one door open or the other. It's both doors are open. There's a superposition of one door open and the other closed, and the other door open and the one closed. And this is the what the quantum description tells you, the quantum state. If you follow the evolution according to the Schrödinger equation, or according to unitary evolution, as it's called, that will be what happens. And so the cat now goes through a superposition of going through both doors. And so this is my humane version of Schrödinger's cat, which is depicted in this picture here. Well, you have to say that something has changed before the level of the cat. And I want to explain how quantum mechanics deals with this issue in the conventional way in which this theory is studied. Oh dear, I really haven't got the hang of it, have I? That's the wrong one. That's it. This picture is one I drew. Well, it was basically originally, at the back of the book you'll see the original version, which was a transparency I used for a lecture I gave in Denmark at Odense, which was the birthplace of Hans Christian Andersen. And I had been invited by the Hans Christian Andersen Society to give a talk to them with the bicentenary of his birth was coming up. It wasn't quite the bicentenary, I think it was 2 years ahead, but they were having lectures by people. And I thought, this is a bit strange. Why do they think of me as an expert on Hans Christian Andersen? Well, I'm certainly not. But then I thought, oh, well, I suppose the reason they've asked me is because the book that Michael generously referred to in his introduction, The Emperor's New Mind, which was a play on the Emperor's New Clothes story. And so I thought, well, I won't talk about that because that was too long ago. And what I'm interested now is in the foundations of quantum mechanics. And I had to try and think of a Hans Christian Andersen story which could somehow reflect the issues there. And I thought of the Little Mermaid as an appropriate illustration. There are various ways in my lecture. There was actually a Schrödinger's mermaid in one place because I think upon one point is the mermaid, when the sun comes up and the first ray of sun which hits the mermaid and it kills her. So I thought if you put a beam splitter between the photon as it comes through and is reflected, then the mermaid will be in a superposition of being alive and dead. But that's not what I'm using the mermaid for here. This is to illustrate quantum mechanics and how it's used. And how is it doing that? Well, you see, the bottom half of the picture is the quantum world, and the top part is the classical world. Now, I have the letter U to describe the quantum world, that is unitary evolution, or the Schrödinger equation. That is the formalism that one uses to describe how the quantum state evolves, how to describe the quantum world. And that is the strange, mysterious, entangled world of these very peculiar creatures that are swimming around at the bottom. You can look at all sorts of strange things, all of which are actual creatures. Some of them are a bit hard to believe, but they're real creatures. And they're supposed to be entangled up in various ways, which is illustrating the quantum world. The top part of the picture is the classical world, C standing for the classical world of classical physics, where you have sort of discrete objects and things that we think we understand and can describe according to classical physics. And the mermaid represents the process whereby the quantum world relates to the classical world. When you make a measurement, say a Geiger counter, the Geiger counter detects a quantum particle, but it makes a click. And that click is a classical thing. You can hear it, you experience it directly, and it somehow magnifies the quantum event up to a classical thing. But it's always been my problem with Geiger counters and things, and with Schrödinger having the same problem with them, is that if it was, after all, a Geiger counter is made up of particles, these are quantum entities, why isn't the Geiger counter a quantum entity? And why does it not, therefore, be in a superposition of clicking and not clicking? Well, that's one way you can go, and you enter the many worlds interpretation of quantum mechanics, which is something I don't like at all, because it doesn't really describe the world we live in. And to me, it's a reductio ad absurdum. It's not the world we want to describe. Now, there are all sorts of other ways people address this question. The Copenhagen school more or less gave up and said, well, you treat the Geiger counter as a class. That's the rule. You treat it as a classical device, and that's what you do. And you don't regard the quantum world as being sort of real in a way. It's a way of enabling you how to calculate probabilities. But that's not the way you actually use quantum mechanics. You have to treat the quantum system as continuing as a real thing, and also with current experiments and so on, it's very hard to maintain the view that the quantum world isn't real in any sense. But let's not go into that here. The way one uses quantum mechanics is you employ the mermaid, who is half quantum and half classical. She has the tail in the quantum world and the top part of her is in the classical world, and she represents the reduction of the state or the collapse of the wave function, which is what happens every time a measurement is made. And it violates the rules of the quantum world, the unitary evolution, and certainly... Well, I drew this picture also with... She's meant to be looking down at the same time on the classical world. So here you see, it's the way it's drawn, it's sort of... She's also, in a certain sense, looking down on us, bringing her experiences from the quantum world to give a new insight into the way the classical world works. So I'm quite happy with all that, but it's not clear how to describe what's actually going on in the world. So this is a picture of how we do quantum mechanics. It's a very peculiar picture. Schrödinger did not like it at all. Clear, but it's the way quantum mechanics work. Here I'm using the particle physicist's way of time. It's going from left to right. I think it's my only other picture where it does that. The quantum state is depicted upwards, and so you think that the quantum state evolves, and then suddenly you do what's called making a measurement, and it has to make a choice between the measurement tells you, or the apparatus tells you, look, you split this quantum state into lots of different alternatives, and then it's a matter of probability which alternative is chosen. There's nothing in the unitary evolution which tells you that, but nevertheless you then evolve by you again, and then it does it again, and it does it. That's the way quantum mechanics describes the world, which is pretty crazy looking, because it's involving two completely different procedures: the reduction of the state, the R process, the measurement process, which violates unitarity, and you have to live with it, which these two procedures are in contradiction with each other. Now, the point of view that I have for a long time adopted for this is that quantum mechanics is an incomplete theory. Not just an incomplete theory, it's actually not quite correct. That is to say, the quantum superpositions, which are things which occur, certainly do occur, but they have a lifetime. And if they're big displacements of mass, then the lifetime is very short. If it's a small displacement of mass, then the lifetime of that superposition can be long. And that is the point of view. And the arguments for this point of view, I have several arguments, and I've seen some others which are attractive to me, but the one that I'm depicting in this picture is where I consider that there is a quantum experiment which you could imagine being done on a tabletop. I was drawing all these diagrams, and I had somebody who was looking at my pictures and telling me what was wrong with the way I was doing it, which was true. I was doing it badly sometimes, but then I think I improved a while. I'm not used to the computer methods of drawing pictures, which is what it was. And he complained that in the apparatus it wasn't entirely clear what the dials were doing and all that. I told him it didn't matter because it's a completely fabricated, invented Heath Robinson type experiment which has no relation to any experiment that I know anybody does. But the point is that this experiment is one which is a quantum experiment in which the Earth's gravitational field is being taken into consideration. Now, there are two ways you might do this in standard quantum mechanics. One way is the way most quantum physicists would do. They would treat the gravitational field just like any other field, and they would do what's called putting a term in the Hamiltonian. Let's not worry about, the physicists here will know what I mean, but don't worry about what it means in detail. It's a quite straightforward procedure, and that gives you a perfectly good answer, which is consistent with the unitary evolution. But Einstein would tell you to do something else, because to Einstein, a gravitational field, and a uniform one, like what the Earth's one is more or less uniform, is equivalent to an acceleration. It's just like being in a lift, in an elevator. When it's moving up or accelerating upwards or downwards, you feel a slightly different change in the Earth's field, and that is just like a gravitational field. It's a fictional field. It's not really a force at all. You could fall with it, and there is no gravitational field. So what you should really do is do your quantum mechanics in the frame of reference, which is freely falling, and then you can transform back and make a comparison between the two. That's fine. If you do that, what you find is almost the same answer, whichever way you do it. But it differs by what's called a phase factor. And I won't go into this because it depends on the formalism, which the physicists here will know what I mean. But the phase factor more or less tells you that it doesn't matter. You can ignore it. Well, that's almost true. It's true if you have only one gravitational field and everything is working in that one uniform gravitational field. You can ignore it and you can do it either way and it doesn't matter. But if you have a superposition of gravitational fields, then you're in trouble because this phase factor is telling you what's called that you have a different vacuum. The vacuum in the two systems is different. And the rule is that you're not allowed to make quantum superpositions from one vacuum and another in another vacuum, a state in one vacuum and another vacuum. It's not allowed. So that it's telling you more or less that to make quantum superpositions of gravitational fields is not allowed. Now that's bad news because no matter how small the gravitational field is, it was telling you you can't do it. And then quantum mechanics would evaporate if you have any gravitational fields. That can't be the right answer. Anyway, if you look sort of carefully at this, and this is an example of the sort of thing that I was trying to consider. Now the time is going up in my good old relativity way. At the bottom I have a picture of a lump of material. This is my Schrodinger's cat, if you like, but it's not a cat, it's just a lump of material, which is put into a superposition of two locations, and they just sit there. And the top part of the picture is indicating the space-time, which is in superposition. And those little curvy things at the two sides are the different accelerations or free falls with regard to the two space-times. And you see that they're different, just a little bit different, and that means that this difference means that they are, according to the Einsteinian view, you've got two different vacua. And so the superpositions are illegal. But the question is, how long does it take for this illegality to show itself? And then you can wave your hands around a little bit and use the Heisenberg time-energy uncertainty relationship and get an estimate for how long it will take before you run into real trouble. And this length of time would be the length of time that that superposition can exist. So after that length of time, it should go to one or the other. And that's the proposal that I've tried to make for a long time. It's very similar to a proposal that had previously been made by Diósi, but he didn't use the general relativity principles to try and motivate this proposal, which is what I was doing here. Now, this is a rather confusing picture, I think, of the space-time in the example I just gave you, where you have at the bottom, the lump is in one location, and then you put it into a superposition, you move the two parts of this quantum state, and each one has its accompanying space-time, and they start to differ from each other. And the question is, how long does it take before one of them has to disappear? Well, the estimate is that you look at the difference between the space-times, and this is now a volume difference. It's a four-dimensional space-time volume, and when that volume difference reaches what's called a Planck scale difference, that is, if you put the gravitational field, Planck's constant, speed of light, all equal to 1, which you just get away with, you have these things called Planck units or fundamental basic units, natural units. In those natural units, when that unit measure comes of order 1, that is when you run into the trouble. And so it's sort of not unreasonable that if you try to combine quantum mechanics with general relativity, that you'll start to run into trouble at that sort of scale. And that gives you an idea of how long a quantum state ought to exist for, according to this scheme. And here we have a cartoon of a type of experiment that Dick Baumeister, who shares his time in Leiden and Santa Barbara in the United States, so he's sort of in a quantum state himself. But he hasn't reduced his state, as far as I know yet, into one or the other, which isn't quite in agreement with this idea, but never mind. Here you see we have a photon, which is emitted by the laser on the left-hand side. There's a beam splitter in the middle. It splits its existence into these two directions, and then the top one, the horizontal photon, goes and is caught in this cavity between mirrors which reflect it backwards and forwards. And you have to keep the photon reflecting backwards and forwards about 1 million times, which requires extremely good mirrors and so on. The other one is another kind of cavity, but where one of the mirrors is replaced by a little tiny mirror of it's about a tenth of the thickness of a human hair, and a little tiny cube, really. And it's a very good mirror, and the photon is reflected backwards and forwards in that, and it's supposed to hit it about 1 million times, and that's enough to move it by about the diameter of an atomic nucleus. And that would be enough, depending on details, for a reduction time of about seconds to minutes, something like that. So the idea is that you have this, because the photon is split between these two existences, the mirror has to be split between two locations, and it's Schrödinger's cat, you see. But it's such a small thing that the thing will not be almost instantaneous as it would be with a cat, but it might be seconds or minutes. And this is an experiment which is ongoing. They've been working at it for, 1 or 2 decades. And the hope is that within the next decade they will have an answer to it. We'll have to see what the answer is. Anyway, that's the end of the faith. I spent more time on these things than I meant to be. But I hope there isn't a real problem with time, because I've probably used it up already. What's the fantasy? Well, there's a bit of an irony here, because I had a lot of trouble with some of the ideas of cosmology, most particularly the inflationary scheme. Let me tell you, this is now my time is going upwards, and we consider this is a picture of the universe. You might ask, what's all the frilly stuff at the back? Well, that's because we don't really know if the universe is infinite spatially or whether it closes up spatially, and it's hard to draw this picture if it's infinite. So I've drawn it as though it's almost closed up, but maybe does something else, we don't know. That's not important with what I want to say. The important thing is we have this expansion. The universe starts with a Big Bang, it expands out, the expansion slows down, and then it starts to accelerate. And this is the observed fact that the two groups at the end of the 20th century found that there is this accelerated expansion, which is a direct consequence, it would be, if Einstein's modification of his original equations that he introduced in 1917, a year after the original version, the cosmological constant, which gives you this accelerated expansion. So that's not disputed. That's the picture that people have. But what's not so clear about it, if you look at the very bottom corner, this is the Big Bang. There was supposed to have been another accelerated expansion right tucked up in that little point. You might ask, why is it not drawn in my picture? Well, the answer is maybe it is drawn in the picture, but it would be tucked into that little black spot at the bottom and you wouldn't see it. So it's the so-called inflationary phase which was supposed to have taken place at the beginning. Now, to me, this was a bit of fantasy, if you like. The reason that I worried about it was largely that it didn't do what it was supposed to in those days. Well, it did some of the things it did, some things which I won't talk about. But the main argument people use that the universe is very, very uniform. It doesn't wiggle, and the curvature of space-time doesn't wiggle all over the place. And the argument was that this is because whatever it was to begin with, if you have the inflationary phase, it would iron it all out. Now, I've never believed that because, well, first of all, I wasn't happy with inflation because it's a very artificial theory. Now, if I can get the next picture. No, I'm pressing the wrong button. Here we are. These are just examples of this is just to illustrate why it is a rather artificial theory, because these are graphs of the potential function for the thing called the inflaton field. The inflaton field was an invention to make inflation work. People used to call it a Higgs field. That was a long time ago, before the Higgs was really discovered, and you can see it's actually nothing to do with it, so let's forget that. But it's a field which needed a new field which wasn't part of understood physics. And people could more or less have this potential function do what you like. It was supposed to have certain shapes to make it do the right things, but nevertheless there's a lot of freedom in that, and there's no theory behind it. So I just have these different examples to show you the sort of thing that people would sort of draw by hand, basically, without some basic theory. But that was why I say it's an artificial theory. But that's not the main problem. The main problem is, does it do what it's supposed to? And I can't make this machine do what it's supposed to. Why is that? Okay, here we're doing. That's it. Now you see, these are space-time pictures of model universes. The first two are representing what you might have with a closed universe, which starts to it expands and then collapses. But in its collapsing, it produces a great mess because all sorts of black holes are formed, and these things, the singularity is an incredible mess. The second one is if you have a collapsing universe, you also have this incredible mess. This mess comes about because of the irregularities in the material in the universe, and these irregularities build up, and this is an example of the second law of thermodynamics acting in the context of gravity, where you have material clumping, and this clumping produces black holes, and the black holes produce an incredible mess. Now, these are the most likely things to happen if you have a random-looking universe which is collapsing. So then you say, turn the time round. I should say, you can put the inflaton field as much as you like in this. It makes no difference to these pictures. If the inflaton field is there or if it's not there, the collapse will look like that mess. It doesn't make any difference. Turn it around, and now we have the Big Bang is a mess. And this is the 10 to the 10 to the 124 different possible Big Bangs you might have. Almost all of them look like that mess at the beginning. Nothing like the universe we have. All sorts of irregularities would appear which are nothing like the universe we see. So it doesn't work to iron out these irregularities. So that was one of the reasons that I had trouble with the inflationary scheme. And this is illustrating the point. See, the point is, the second law of thermodynamics tells us that things get more and more random. There's a thing called entropy, which is, roughly speaking, a measure of randomness, and this randomness is increasing with time, and that's what we see in our normal experiences. Now, another way of stating exactly the same thing is if you go back in time, the randomness gets less and less and less. And so why is it that we don't have an incredibly random Big Bang then? Why don't we have an incredibly unrandom Big Bang? And this looks like a paradox at first, because one of the best pieces of evidence for the existence of a Big Bang is the microwave background radiation, which is coming to us from all directions. And one of the most striking features of this, one of the most earliest things measured about it, is that it has what's called a Planck spectrum, which means that what you're looking at is basically randomized as much as it could possibly be. And that looks like a paradox, because it's saying that the entropy is going down and down and down in the back, and then it reaches a maximum. I regard that as the mammoth in the room. There's something extraordinarily wrong with that, because it has to be a small entropy, yet what you seem to see is a large entropy. And the answer is in these pictures here. If you consider a gas in a box, that's the top four. As time progresses, now time is going horizontally again, so this is the particle physicist's direction of time going horizontally, and we see that if you put the gas in a little compartment in the corner, when you open the compartment, it spreads up over the box and gets more and more uniform. Well, that's consistent with the universe being uniform, so that's fine. But suppose you have gravity. Now this is a bigger box. It's looking at a lot of stars in a galactic scale box. Now what happens when the entropy increases? It clumps and clumps and gets more irregular and ends up with this black hole as being the huge increase in entropy. So what you see is bottom left-hand corner together with top right-hand corner, a very uniform universe, which is really high entropy for the matter, but very low entropy in the gravity. And that's where the second law of thermodynamics works for us, if you like. And here's an example of that. We live off the sun being a hot spot in the dark sky, and that's what we live off, not the energy. We don't get energy from the sun, despite what people say. because the energy that we get from the sun goes all the way back out into space again, just as well it does, or we would fry ourselves in a day or two. So that's good. But what's also good is that the entropy comes to us in a low entropy, the energy comes to us in a low entropy form and goes away in a high. It's a point made by Schrödinger a long time ago. The energy goes out in a high entropy form. Many, many photons go out carrying the same energy. There's lots of higher energy photons coming in, and we live off that. So this is an example showing us that the clumping of the material into stars is really what we live off. Okay, there are thermonuclear reactions and things going on, but the important point is the sun's there at all, which came about because of the gravitational clumping. So that's the point about that. Now I'm having my troubles again. I press this thing and it doesn't move. Here we are. Now this is a black hole. So this is my picture of a black hole, which is space-time, time going up again. I won't say much about the picture, except that you can see what's going on because of the light cones. Those are these cones which are describing the major part of the geometry of space-time. And so we have to imagine when we think of space-time that every point of space-time has a little cone which is telling us how light would behave if there were any light there. It doesn't have to be that there's a photon there or anything. These little cones are part of the structure of the space-time. And this structure of the space-time is telling you how light would behave, and that is almost all the metric information. And this is telling you what the light cones mean. The left-hand picture is a spatial picture of a light flash coming from a point, spreading out. The middle picture is showing the space-time picture, same thing, but now you see the cone. You have the past cone of light coming in, future cone light going out. And you have to imagine that your space-time has one of these cones which is really sort of drawn in the tangent space. It's a local structure at each point in space-time. So that's the way to think of space-time geometry, but not quite all of it. It's the geometry of the light cones, which is the conformal geometry of space-time. What do I mean by conformal? Well, conformal geometry is the geometry of angles where you don't care about distances. It's a very beautiful kind of geometry. I've always been attracted by it. It has many aspects to it which are very elegant. In the space-time context, it's more or less telling you the light cones. The extra information is how clocks behave. So you have to have these rather sort of bowl-shaped surfaces which tell you, if you have a lot of clocks which start at this point, the bottom, x, and then they're all supposed to be identical clocks but moving with different speeds, and the first tick and the second tick and the third tick are described by those surfaces. And the way those surfaces are concentrated, whether they're spread out or concentrated, is the additional measure. I should say that in general relativity, in four-dimensional space-time geometry, the metric is described by a quantity which has 10 components, 10 numbers you need to characterize it. Roughly speaking, 9 of them are telling you where the cones are, how they're pointing, and so on. The 10th one is the scale. The 10th one is giving you the metric structure. The 9 tell you the conformal structure. So it's most of the geometry. That's the point. It's most of the geometry also in the sense that it's this geometry is telling you how light behaves. Anything to do with massless particles. You see, photons don't have any mass, and they are described classically according to the wonderful equations of Maxwell. Maxwell equations describe electricity and magnetism and how those two fields interact with each other, and with the conclusion that they will propagate each other through space with the speed of light, and that is light. So it's a very remarkable discovery. Faraday basically doing the experiments and speculating about this, and then Maxwell producing these beautiful equations which fit together in this wonderful way. But the point I want to make is that the Maxwell equations only need to know the cones. You don't need to know the scale. They're completely invariant under making it bigger and smaller here and here. As long as you leave the cones where they are, you make the scaling bigger and smaller here and change any way you like. It makes no difference to the Maxwell equations. This is also true of the other physical fields, the strong and weak interactions. The Yang-Mills theory also have this feature. What's different, though, is that in Maxwell theory, you don't have massive particles involved, whereas in the weak interactions you've got particles with mass, and so you have to worry about that. The point I want to make about mass is that it's mass that really gives you the scale. And in measurements of space-time structure, which are now extremely good, and they depend on the very precise clocks that we have now. Your GPS, which tells you where you are and how to drive your car to the right place, depend on having extremely precise clocks. And clocks are so precise now that you can even measure the difference in the clock rate between here and here. You should go up about 1 centimeter. And that difference in the clock rate in the different gravitational potential you've got can be measured with clocks. Fantastic. Now, this depends, the extreme precision that you have in these clocks, which is really good because you can test how wonderful Einstein's theory works. The extreme precision comes from, ultimately, the two most fundamental equations, or famous equations, of 20th century physics. One of them, of course, has to be Einstein's E equals mc squared. The other one is Max Planck's E equals h nu, nu being a frequency. You put the two together, this tells you a mass and a frequency are equivalent. And that tells you that if you have a particle which has a very definite mass, suppose it's a stable particle, it is a clock, just through those two fundamental principles. So it has an oscillation which is completely determined by its mass. And this is a very fundamental notion. Of course, you can't measure that frequency directly. It's too high, and you can't really access that. But ultimately, the precision in these atomic and nuclear clocks comes ultimately from this fact. So this is what I'm saying, that if you have massive particles, you have incredibly good clocks, and therefore you need the full metric. But if you don't have mass, then you don't have clocks. And that's the converse to this. And there are two places where you could argue that you don't really have clocks, because you don't have mass. Now, the first place that let me talk about is the very remote future. In the extremely remote future, I'm going to wait for Google years and longer. All the black holes are gone. There's basically, essentially, photons running around all over the place, and they don't care about the metric. Now, it's a thing that I played around with a long time ago in relativity to try and talk about gravitational radiation, electromagnetic radiation. And a nice, convenient trick was to use a conformal transformation or a conformal rescaling. It's an example here, which you can see with this very beautiful Escher picture. You must imagine these fish, the black ones and the white ones, inhabit a world which is what's called hyperbolic geometry. Don't worry too much about that. But the picture here is a conformal picture. So you must think of the geometry as being conformally, you think of the eyes as the fish, and those eyes are exact circles. And no matter how close you are to the edge of the picture, they remain circles. But to the fish, that edge, the boundary, is infinity. That's the infinity of their world. But the way you've represented it is a conformal picture, so the angles are correctly represented, and the conformal geometry is, I think my thing is moving here. The conformal geometry is correctly represented, but you see I've changed the scale as you get near the edge. But if you have things which don't notice the scale, then the boundary is just like anywhere else. And so infinity to the photons is like anywhere else. And why should they worry? They get right out to infinity and they say, well, what's up there? Why should we stop now? So that's one place where the idea of looking at conformal geometry is a fruitful, not just mathematically useful, but seems to be saying something about the physics. That the physics seems to say the universe has unnecessarily come to an end, if you like. You might say, what's on the other side of this world? What is the world to unmask this entity, which doesn't have a scale to it, on the other side of that boundary? Okay, well now I want to describe the other end of the picture, which is the Big Bang. Now if you go down to the Big Bang, I used to have a way of talking about the very special nature of it, which is just a hypothesis. I would say the Weyl curvature, that's W-E-Y-L, the great German mathematician, Hermann Weyl, who introduced the idea of a conformal curvature. And if this curvature is non-zero, then you have a conformal geometry which is non-trivial. And the Big Bang seems to have had a zero Weyl curvature. Now, so that was a hypothesis. But my colleague Paul Todd had another way of saying this, which is a much more elegant way than mine, which was to say, well, the Big Bang, you stretch it out. Instead of squashing it down, which is what I've done for the future boundary to infinity, look at the past and stretch it out. And that stretch, again, you might say, well, you have lots of massive particles right at the early universe. But no, because the energies get so big, when you get run down close to the Big Bang, the energies are so enormously large that they effectively have no mass. So they might as well not have any mass. Their mass becomes totally irrelevant. So again, you have a place where massless physics is the important physics. So again, you could say, well, those particles don't really have a mass because they're so energetic, and they come from a place which just looks like an ordinary boundary. And they might ask, well, where do we come from? There's nothing wrong with this boundary. There should be something on the other side. So this picture puts the two together. Here I have the top part of the picture is representing a Big Bang, and the bottom part of the picture represents an infinity. I should explain why I stuck the two together, which has to be in the next picture. This is my picture of... I'm really having trouble with this. Why am I not moving the picture on? There we go. This is my picture of conformal cyclic cosmology. The one just above the middle, on the left-hand side, is meant to be our eon. That's a small version of the picture I had at the beginning of this section, where the universe has its Big Bang, and then it does this exponential expansion. But what I'm saying is that as far as the relevant physics at the two ends, it should be the conformal geometry which is relevant. So I can stretch out the Big Bang, I can squash down infinity, and do that. And I imagine that I'm calling it our eon, that's that one. There's one below it, which is the eon prior to ours. There was an eon prior to that. There will be another one after ours, and they keep on going. So that's the picture I have in what I call conformal cyclic cosmology. And the join between these eons is smooth if you're interested in only the conformal geometry. Of course, the metric changes, and in fact, it does a huge jump. It goes from very rarefied zero density to very concentrated infinite density. But it does this in a conformal way, which is completely smooth in this picture. And so that is what I call conformal cyclic cosmology. So although the fantasy in the book was aimed at other people's theories, which I regarded as fantastical, in the 13 years between when I gave the lectures at Princeton and finally started writing my book, I had this crazy idea of my own, which I regarded as my own fantastical scheme. And so I have to shift my view as to the word fantasy. I say we need fantasy. The world is so strange that if we don't play with fantastical ideas, as with quantum mechanics, we're never going to get the answer. So you have to play with fantasy, and the question is not so much whether it is fantastical, the question is whether it's the right fantasy. So that is the challenge. So I'm perfectly prepared to say that my ideas are crazy. The question is not that they're crazy, but are they the right crazy? And so that is the challenge. But this gives you an idea of the scheme which is described in the book. The last chapter, I have three sections. One is on twistor theory, which is my own sort of version of what one's trying to do. The string theory people have a different way of trying to do it. And the middle section is to do with I had some pictures from that, to do with the extension of quantum mechanics, which brings in these ideas from gravity. And the final chapter is this scheme here of conformal cyclic cosmology, which I believe has some observational evidence in its favor. But that is the kind of thing that we have to discuss. We haven't going to do that in Warsaw in a few days' time to see how far we can get with that. Thank you very much.
Thank you very much for this fascinating lecture. We now have a few minutes for questions, so we have our people gathering your questions.
Yes.
Okay, so there's one question about black holes.
Yes.
So what is your take on the information loss paradox in black holes? Do you think that it's lost, or is it something?
Yes, there's the thing called the information paradox. It originated with Stephen Hawking's analysis of black holes, in which he showed that not only should there be an entropy, this was an idea of Bekenstein's originally, and Stephen Hawking made it more precise. But he also made it more consistent with thermodynamics by introducing a temperature as well. And in his initial discussion, he considered that information was swallowed by the black hole and was lost. Later on, he changed his mind and considered that the information couldn't be lost and had to be regained. Now, in a certain sense, the information, if you believe quantum mechanics at that level, that is to say, if you believe in unitary evolution, then you cannot lose information. And Stephen Hawking originally tried to modify the unitary evolution in a way which said that information was restored. That the information was indeed lost, but that the unitary evolution had to be broadened in a way that he introduced. But then he subsequently changed his mind. Now, in my view, he was completely wrong to change his mind. He was right the first time. Information is lost, and it's very hard to avoid this conclusion when you look at conformal diagrams of what happens and how this information can somehow be repeated outside. I think violates standard quantum ideas. It certainly violates unitarity for information to be lost. But yet, since I don't believe in a gravitational context that unitarity is preserved, I think it has to be violated. It's no problem for me. But in the context of what I'm saying, it's a very important feature that information is lost, because I don't know if it's another of the questions on the pieces of paper, but whether it is or not, I need to answer it. I have been talking about the second law of thermodynamics, and the second law of thermodynamics says that entropy increases with time. So you might say, why is entropy not increasing up this cylinder and keeping on increasing? And I worried about this for quite a long time. And then it occurred to me that Stephen Hawking's information loss is a crucial thing, because when you ask about entropy, you need to have, what do you mean by the entropy? Now, the entropy depends on what degrees of freedom you take into consideration. When a black hole swallows degrees of freedom, it's what happens in information loss, then you have to renormalize your entropy. You say that the entropy notion that you were using previously, before that black hole evaporated, is now not the right entropy, because it takes into account all those degrees of freedom which were swallowed by the black hole. And now you say, I don't care about those degrees of freedom anymore, so I now will renormalize my entropy. There is no violation of the second law, but I say this is not the useful notion of entropy to use. I should use an entropy notion which removes those degrees of freedom from the picture. And then as the black holes, which represent by far the largest contribution to the entropy in the universe, even now, this will increase as time goes on, this is what you have to deal with. And when the black holes disappear, you have to change your notion of what you mean by the entropy, and that's how it comes down to the low value that you have, basically in the gravitational degrees of freedom, in order to make the picture consistent. So not only do I say that information must be lost, I say it is not a paradox. It's not a paradox because unitarity is violated, and it has to be violated, in my view. It's a paradox if you believe unitarity has to be true under all circumstances. If you don't believe that, it's not a paradox. It's just a fact of the world. And it's an essential fact in this model. because otherwise you would have trouble with the second law of thermodynamics.
Thank you very much. So now a question about the big numbers.
Yes.
So can you tell us how
How that number comes about?
How does this
Yeah.
huge number
Sure.
expressing the improbability of Big Bang happening, how does it come about?
Yes. Well, again, it's this Bekenstein-Hawking formula. And it is the entropy in black holes, which is absolutely huge. Now, you see, the Boltzmann definition of entropy is a logarithm. You have the entropy, is usually called S, is a logarithm of a phase space volume, which has to do with degrees of freedom. Now, the logarithm means it's you taking all the different things that can happen, and this number, it's a volume in phase space. I'd have to describe what phase space was and all that, but let me say it's basically counting the number of degrees of freedom. And the number of degrees of freedom is measured by the entropy, and because of the logarithm of that formula, when you want to know how improbable a state of low entropy is compared with a state of larger entropy, you have to take an exponential. And that exponential is raising to a power. So that is one of the powers. That is the 10 to the power 10 to the power. It's really e to the power 10 to the power 124. But as I said, the e and 10 make no difference. And the reason it's e is because the logarithm in Boltzmann's formula is a natural logarithm. And so the inverse of the logarithm is an exponential. So that's e to the something. Now, where does the 10 to the 124 come from? Well, that comes from the number of particles in the observable universe. You have to see. Well, you need to know in the appropriate units. You see, the number of protons in the observable universe is something like 10 to the 80. And so you have 10 to the 80, and then you say another factor because the proton, how many units are there? I mean, it comes from the Bekenstein-Hawking formula. It's basically the inverse of that formula, which is telling you how big the volume in the phase space is because of the Bekenstein-Hawking formula. I don't think I could go into any more detail except to say that's where it comes from. You see, the most likely universe that you could construct, you take the collapsing universe, the pictures I had with the great mess as the universe collapses, and that mess is a congealing of black holes. And the biggest mess you could get is with one black hole. And that one black hole, you see what is its entropy according to Bekenstein-Hawking, and you say if you've got 10 to the 80 protons, actually you need more than that because it's the dark matter. So 124, I used to say 123, but if you put dark matter in as well, then the number goes up because most of the matter in the universe is in the form of dark matter. So you include not just protons and things, but the dark matter also. And so you have a number like 10 to the 124 in natural units, and then you say exponential because of the Boltzmann formula. That's where it comes from.
Okay. Thank you very much.
What was that?
Okay, let's move to the questions from the adversary. There's there's quite a lot of them, and there are many of them concerning consciousness. And its role in the quantum world. We know that you have your own viewpoint.
You want me to say? I'll say that. One or two words about that, if you like. See, that's not mentioned in the book, except at one place. And let me just make this point. I take an objective view of the collapse of the wave function. So there is a view that sometimes people hold, and Wigner presented this point of view. I think even von Neumann presented this point of view, that somehow the collapse of the wave function is when a conscious being looks at something. So when these alternatives are presented to a conscious being, that somehow the choice is made. Now, this is not my view. My view is it happens objectively in the world. It has nothing to do with any conscious being coming and looking at the system. It's reducing spontaneously by this gravitational effect. But I do have a converse thing to say, which is almost the opposite. And that is the argument, which I do not describe in the book, I should say this, but I do mention it. Because when the universe, I have this crazy-looking picture, which I suppose I could go to if I could master this machine, which I can try. Let's try it. Yeah. Here we see the universe is bifurcating, and it makes a decision between which of these two branches to become. And that is, in current quantum mechanics, would be a random choice. Nevertheless, it is a choice of a sort, which is made by the universe. Now, the view that Stuart Hameroff, my colleague, and I have, is what consciousness is, in a sense, is somehow this process orchestrated in some way in the brain. That somehow this is what we might call an element of proto-consciousness. The universe is making a choice, and in that choice is a moment of proto-consciousness. And when I say proto-consciousness, I mean the building block out of which the phenomenon of genuine consciousness is constructed. So the building of consciousness, if you like, has its bricks are these processes. Now, these processes are not at a tiny scale necessarily of... See, often people did kind of argue that maybe free will could come about because particles are making choices. But it's not particles that make choices, because they don't make choices on this scheme, because the particles are much too small. The choices are made on a much bigger level when there is considerable mass displacement. Now, when I can say considerable, it's still small. But in the brain, the argument goes that there are these little structures called microtubules. I learned about them from Stuart Hameroff, and the scheme that we developed is with Stuart Hameroff. And the idea is that these microtubules are important in the strength of synapses, and that the phenomenon of consciousness has to do with quantum coherence taking place and this collapse process, which would be the building blocks of consciousness. Of course, this is a long way from experimental confirmation or refutation, but it's a scheme that we've been working on for several decades by now. That's all I think I should say on consciousness. The only thing in the book to do with it is in relation to this picture, and there's only a reference to a couple of articles that Stuart Hameroff and I have which mention this idea. I should talk about physics, I think, from this point onwards.
Okay, thank you very much. And there are a few practical questions from students of physics and mathematics. So could you give some good advices how do you come up with new ideas, and what is more important, the, say, mathematical rigor or just fantasy, crazy ideas, imagination?
Well, of course, you need all those things, don't you? I mean, it's impossible really to give advice in a few words. I mean, advice I was giving a little earlier to people is do things that excite you, even if you don't see... And I mean, I can't give universal advice, because you want people who do things because they think they're doing good in the world, and that's very important. So often, if you think you can make an influence for good, that's extremely valuable. But I think ideas in physics and related like that are not motivated by moral issues. They're motivated by what you find exciting in the way the world operates, and to try and see more deeply into the laws which govern the way the world operates. And I've always found that exciting. But on the other hand, I've always found mathematics exciting and very beautiful and attractive. And my early studies were in pure mathematics. So when I did my PhD in Cambridge, it was in pure mathematics. But I was very interested in the physics, and I went to lectures by Herman Bondi on general relativity and cosmology, which were beautiful, wonderful lectures, very exciting. I went to lectures by Paul Dirac on quantum mechanics, beautiful in a completely different way, very gently organized, logical, and I found fascinating. And I learned my quantum mechanics from Dirac. Who better to learn my quantum mechanics from? And I went to a third course, again, nothing to do with what I was doing, which was a course on mathematical logic, where I learned about Turing machines, Gödel's theorem, and I more or less formulated my opinions about consciousness and how it relates to understanding and computational procedures. And these things developed in books that I've written later on. So I guess that, you might say, the moral from that is go to lots of things which aren't to do with what you're supposed to be doing. Now, I'm not sure that's a good moral to suggest. I think in my first year and a half, maybe 2 years, I think, when I was trying to do my PhD, I didn't worry too much about what I was doing. I just did what interested me. What interested me was, a lot of it was physics. And my friend there, Dennis Sharma, who was a bit older than me and who knew an awful lot of physics and taught me a lot of physics, and I learnt a great deal from him. I don't know. I can't give general advice, because I can give you my own experiences. My own experiences are maybe unusual in one respect or another. I grew up in a family where there was a lot of interest in science. My father was human genetics was his area, but he was also very interested in mathematics. My older brother was very interested in physics. I learned a lot of physics from him. And that doesn't always happen. So people may not have those advantages. Nevertheless, I think there's a great deal in physics which is exciting. And I think do what you find exciting and interesting. But there's a limit to that, because you can't necessarily find an area where there's a spot which where you can make real advances that other people haven't thought of. And there's a lot of luck involved in that. You can't get away from the fact that there is an enormous amount of luck involved. I can't give advice to say to be lucky. That's hardly a useful piece of advice, is it?
Okay, thank you very much. Well, unfortunately, we are not photons, so we don't have an infinite of time at our disposal. So we have to conclude here. Professor Penrose will still be here for a few minutes signing the books. So let's thank him for the great lecture.